Yet for centuries, humanity has grappled with this profound question. What is it, really?
As a fundamental force, yeah.
Yeah.
The very fabric of our cosmos. Yet its true nature has always been, well, a source of intense debate.
And that's exactly what we're getting into today. This deep dive is all about kinetic gravity, often called push gravity. We're going to explore a fascinating sort of long-discarded idea where gravity isn't an intrinsic pull from within matter,
Right.
but an extrinsic push from some unseen, all-pervading medium.
Something outside pushing in.
Exactly. And our mission, to figure out why this seemingly intuitive concept ultimately failed, and yet why it still, tempts some researchers even now.
Well, historically, the quest to understand gravity, it really followed two very different philosophical paths.
Okay.
The one we're most familiar with, the dominant path, sees gravity as an inherent property of matter and energy itself.
Right, like Newton.
It started with Newton's action at a distance, objects just mysteriously pulling each other across empty space, which actually he himself found deeply unsettling.
Yeah, I remember reading that. He wasn't happy with the why.
No. And this path eventually led to Einstein's general relativity, where gravity isn't even really a force in the traditional sense.
It's the shape of space-time.
Exactly. It's the curvature of space-time caused by mass and energy. Objects just follow the straightest possible paths, geodesics, through this curved geometry.
Okay, so that's path one. What's the other one?
The less traveled path, the one we're talking about today. Kinetic theories. These imagine gravity as a mechanical phenomenon.
Mechanical, like billiard balls.
Sort of. Caused by pushes from an unseen medium that fills the entire universe. So instead of two massive objects pulling each other.
They're actually being pushed together.
Precisely. And you can immediately see the appeal, right? No mysterious, unexplainable action at a distance. It's all just, straightforward pushes and shoves. Seems more intuitive somehow.
Yeah, it does feel a bit more tangible.
Exactly. But this highlights a critical point right from the start. Kinetic gravity, at its core, isn't just a theory of gravity. It's fundamentally a theory of an undiscovered, all-pervading form of matter.
Because you need something doing the pushing.
You absolutely do. If you're going to explain gravity as a push, you need something doing the pushing. And the very existence of this hypothetical substance and the really extreme properties it would demand, that's what makes it so elusive, almost phantom-like.
Okay, so phantom matter pushing things together. How was this ingenious illusion, as you called it, how was it supposed to work?
Well, the most famous version, the Fatio-Le Sage model. Nicolas Fatio de Duillier around 1690, and then Georges-Louis Lesage picked it up in 1748. It's really quite clever, a sort of masterclass in deductive reasoning.
So what's the core idea?
It's deceptively simple, really. Imagine the universe is just uniformly filled with a constant flux of incredibly small, unseen particles. Lesage called them ultramundane corpuscles.
Ultramundane, like beyond the world.
Yeah, meaning coming from beyond our world, from everywhere. And they're moving at extremely high speeds in absolutely every possible direction. Just a constant isotropic hail.
Okay, like cosmic rain from all directions.
Pretty much. Now, picture an isolated object sitting in this cosmic torrent. It's being bombarded equally from all sides by these corpuscles.
So all the pushes cancel out?
Exactly. All those pushes perfectly balance, resulting in no net force. The object just sits there or keeps moving in a straight line if it was already moving. Newton's first law holds.
Right. But what happens when you add a second object?
Now the symmetry is instantly broken. Each object acts as a shield. It intercepts some of the corpuscles that would have hit the other object from that specific direction.
So it casts a sort of corpuscle shadow.
A shadow, exactly. This creates an imbalance. There are fewer impacts on the side facing the other object because it's blocking some of the incoming stream.
Which means there's more push from the outside.
Precisely. More push from the outside than from the direction of the other object. The result is a net force pushing the objects towards each other.
And crucially, this works in both directions. Both objects cast shadows on each other.
Yes, they both get pushed towards each other. So in this model, what we perceive as gravitational attraction is fundamentally an illusion. It's a push, not a pull.
A shadow effect.
A shadow effect causing a net push. And what's truly remarkable is that Lesage showed mathematically that this pushing force would vary inversely as the square of the distance between the two bodies.
Just like Newton's law.
Exactly like Newton's law of gravity. It seemed to explain it mechanically.
Okay, that is clever. But there's always a but, isn't there? What did these particles have to be like for this to work?
Ah, yes. To make this push-shadow mechanism actually work and replicate observed gravity, Fatio and Le Sage were forced to assign some truly extreme and very specific properties to their corpuscles. This is where it starts to get, well, let's call it a catalog of extremes.
Okay, I'm ready. What's first?
First, size and penetration. If gravity was to act on the total mass of an object, not just its surface area, which we know it does, these corpuscles had to be extraordinarily small.
Tiny.
Unimaginably tiny, able to pass through macroscopic bodies like plants or even us, almost entirely unimpeded. They had to interact exceedingly rarely with the actual matter they pass through.
So they just zip right through most of the time.
Almost all the time, only interacting with a tiny fraction of whatever makes up matter.
Okay, extreme smallness. What else?
Speed. There's a drag problem. Any object moving through this constant flux, this cosmic wind, would experience resistance, right? Like running into a headwind.
Yeah, it would slow things down. Planets would spiral into the sun.
Exactly. And since we observe orbits have been stable for billions of years, that's a huge problem. So Le Sage has reasoned the corpuscles must travel at immense speeds to minimize this drag effect.
How fast?
He initially suggested the speed of light, which was already incredibly fast for the time. Later, he revised that upwards, suggesting speeds maybe as high as 105 times the speed of light.
10,000 times faster than light.
Sorry, 100,000 times, 10 to the power of 5.
Whoa, okay, that sounds problematic even before Einstein.
Deeply problematic, yes.
Yeah.
And as we'll see, even that wasn't enough to really solve the drag issue.
All right, tiny, super, super fast. What else? Collision properties.
Yes, the collisions couldn't be perfectly elastic, like perfect billiard balls bouncing off. If they were, they'd just bounce off with the same energy, and there wouldn't be a net push resulting from the shadow.
Okay, so they have to lose some energy in elastic collisions.
They had to be at least partially inelastic. But specifically, to make the math work out to an inverse square law push, Le Sage proposed a very contrived scenario.
How contrived?
The collisions had to be completely inelastic, meaning the corpuscle stops or gets absorbed when hitting a surface head-on, perpendicularly, but perfectly elastic, bouncing off perfectly if they just grazed the surface tangentially.
Wait, so it depends entirely on the angle of impact. That sounds artificial, like they were just making it fit.
It does seem like a bit of a contrivance, yes. Bending the physics to fit the desired outcome.
Okay, so tiny, ludicrously fast, and weirdly specific collisions. Is that it?
One more big one. Energy. Critics later calculated the energy implications. To produce the observed strength of Earth-Sun gravity, the energy density of this Le Sage flux, this stream of corpuscles, would have to be immense.
How immense?
Roughly 10 to the 113 joules per cubic meter.
Okay, numbers are hard to grasp. How does that compare to something?
To give you some perspective, that's about 17 orders of magnitude greater than the energy density of sunlight hitting the Earth.
17 orders of magnitude. That's a billion times more energy packed into space than sunlight.
Something like that. A truly astronomical, almost incomprehensible figure. Just this constant, incredibly energetic background flux filling all of space.
Right. Okay. That list of properties is definitely extreme. But you mentioned something earlier, a surprising prediction about matter itself.
Ah, yes. Perhaps the most profound deduction from the theory, and weirdly prescient. If these corpuscles had to penetrate matter easily to create a mass proportional force, what does that imply about matter itself?
That it can't be very solid, that it must be mostly empty space.
Exactly. For the corpuscles to zip through, matter itself has to be almost entirely void. Fatio wrestled with this. His early models were like infinitely small, solid balls. Then he thought maybe crystal lattices, before settling on atoms being like connecting lines or bars, essentially like a very, very fine net or a cage structure. Mostly empty space.
A cage like atom.
Yes. And Le Sage later tried to estimate the dimensions. He figured these atomic cages would have a diameter maybe 10 million times greater than the distance between the bars forming the cage.
So incredibly sparse.
Incredibly sparse. And the bars themselves, maybe 10 to the power of 20 times longer than they were thick. Like unbelievably thin threads making up this structure.
Wow. And this is fascinating
because this purely logical deduction, that matter must be mostly empty space, to allow penetration strikingly prefigured the later experimental discoveries of the nuclear atom by Rutherford and others more than a century later.
Even though the whole kinetic gravity idea was wrong.
Even though the premises were flawed, yeah. It's a remarkable testament to the power of just following deductive logic, even if your starting point is off track. It stumbled onto a truth about matter for the wrong reasons.
That is amazing. Okay, so it had this intuitive appeal, it matched Newton's law, it even accidentally predicted the empty atom. Why did it fail so spectacularly?
Well, despite its ingenuity and that weirdly accurate prediction, the Fatio-Le Sage theory was ultimately abandoned. And it wasn't just one single flaw, it was more like a cascade of unobserved and frankly catastrophic physical consequences.
Things the theory predicted that just don't happen.
Exactly. Major thinkers like James Clerk Maxwell, Henri Poincaré, Hendrik Lorentz, they really dug into the physics of it in the late 19th and early 20th centuries and exposed these fatal vulnerabilities.
So what was the first big killer? You mentioned drag earlier.
Right, the orbital drag catastrophe, that headwind problem. Any object moving through this corpuscular flux must experience a resistive force slowing it down. It's unavoidable if the particles carry momentum.
Because you hit more on the front than the back?
Precisely. Impacts on the leading surface would be slightly more frequent and energetic than on the trailing surface. This creates a drag force.
And the consequence?
Catastrophic for the stability of the cosmos as we know it. Every single planet, every moon, would gradually lose orbital energy and spiral into its parent body, the Earth into the Sun, the Moon into the Earth.
Over geological time.
Over astronomical timescales, yes. But it would happen. And this starkly contradicts the observed stability of our solar system over billions of years. It also fundamentally violates the law of inertia for orbiting bodies.
Didn't Le Sage try to fix that with the superfast particles?
He did, hoping the immense speed would make the drag negligible. But Poincaré later showed mathematically that even those superluminal speeds didn't actually eliminate the problem, they just sort of postponed the inevitable collapse. The drag is reduced, but it's still there, and over long enough times, it adds up.
Okay, so drag is bad. Problem one. What else?
Well, remember those necessary inelastic collisions? The ones needed to create the push.
Yeah, the ones that weren't perfect bounces.
Well, basic physics tells us that when you have an inelastic collision, kinetic energy isn't conserved as kinetic energy. Some of it gets converted into other forms, usually heat.
Ah, so the objects being bombarded would heat up.
Exactly. And this leads to what Maxwell famously articulated as the thermodynamic catastrophe.
Thermodynamic catastrophe. Sounds dramatic.
It really is, because remember that absolutely immense energy flux required to produce gravity.
The 17 orders of magnitude more than sunlight thing?
That's the one. If even a tiny fraction of that colossal kinetic energy is converted to heat, with every interaction inside matter, which must happen with inelastic collisions, calculations show the consequences would be, well, explosive.
How bad?
Every object in the universe, planets, stars, you, me, would be heated to an incandescent temperature in literally a fraction of a second. Maxwell concluded it would simply vaporize all matter almost instantly.
Right, and we're clearly not vaporizing, so that doesn't happen.
Definitely not observed, no. Our planet remains quite comfortably solid and not boiling away. So another catastrophic prediction failure.
Okay, so you've got drag making orbits decay, and you've got heat vaporizing everything. Those seem pretty fatal on their own.
They are. And worse, they're interconnected in this really nasty way, often called the Le Sage trilemma. The model is basically trapped between three mutually exclusive requirements. It can't satisfy them all.
A trilemma. Okay, break it down. What are the three horns?
Okay. Horn one. To get a gravitational force of the observed strength, you need a high-momentum corpuscular flux interacting inelastically with matter. That's required for the push mechanism.
Right, need the push.
Horn two. Those necessary inelastic interactions inevitably lead to catastrophic heating, violating observed thermodynamics. We'd all be vapor.
Okay, the heat problem.
Horn three. To avoid the other catastrophic problem, orbital drag, the corpuscles must have those extreme superluminal speeds.
The speed fix for drag?
But, and here's the trap, making the particles faster only makes the heating problem exponentially worse. Kinetic energy increases with the square velocity, so cranking up the speed to reduce drag vastly increases the energy dumped as heat.
Oh, wow. So you can't fix drag without making the heat problem infinitely worse, and you need the interactions that cause the heat to even get the force in the first place.
You got it. The theory cannot be adjusted to solve one fundamental problem without catastrophically exacerbating another. It's utterly trapped in a corner of its own making, its own parameter space. There's no viable combination of properties.
That seems pretty conclusive. Were there other issues too?
Oh yeah, beyond those main killers, there were other significant challenges. One was this idea of self-shielding, or gravitational absorption.
Self-shielding.
Think about a really large, dense body, like the sun. According to the theory, the outer layers should shield the inner parts from some of the incoming corpuscles, right?
Yeah, the shadow effect again, but inside the object itself.
Exactly. Which means gravity shouldn't be perfectly proportional to the total mass. The inner mass should contribute slightly less to the gravitational field than the outer mass because it's being shielded.
Has that ever been observed? Does the sun's gravity work differently for things deep inside it?
It has never ever been found.
Yeah.
Gravity appears to be perfectly proportional to mass, regardless of density or size. People looked for this effect, especially during solar eclipses, thinking the moon might show some gravitational anomaly when passing through the sun's shadow, but nothing.
So, another failed prediction. Any others?
Well, that shielding mechanism also implies that there should be a finite limit to gravitational force. Eventually, if an object gets dense enough, it blocks all the corpuscles from one direction. You reach a maximum possible push, it saturates.
And real gravity doesn't do that.
As far as we know, no. Newtonian and Einsteinian gravity predict that the force increases linearly with mass without any known limit. There's no saturation effect observed.
Okay. And you mentioned relativity earlier.
Right. The whole theory is fundamentally incompatible with Einstein's special relativity. It absolutely requires a preferred absolute frame of reference, the frame where the corpuscle flux is isotropic, which relativity abolished. There's no universal rest frame.
And the faster-than-light particles are obviously a big no-no in relativity, too.
A huge violation of the cosmic speed limit, yes.
Yeah.
So by the early 20th century, with the rise of thermodynamics, electromagnetism, and especially relativity, kinetic gravity just didn't fit into the modern physics framework.
So the lesson here, what would you say it is?
The lesson is pretty clear, I think. The collapse of classical kinetic gravity showed that its appealing simplicity, that intuitive mechanical feel, was really an illusion. It masked deep, irreparable inconsistencies with other established physics.
It has to work everywhere.
A successful theory has to be consistent across all relevant domains of physics, mechanics, thermodynamics, relativity, not just the single phenomenon it's trying to explain in isolation. It failed that test badly.
Okay. So it died a death by 1,000 theoretical cuts. But you said it's had a bit of a comeback. Why?
Well, for nearly a century after its classical refutation, kinetic gravity really was relegated to the history books, a curiosity. But then the late 20th and early 21st centuries brought this new intellectual landscape, profound new mysteries in cosmology that opened the door, just a crack, for unconventional ideas.
What kind of mysteries?
Two big ones, mainly. First, the galactic rotation problem, which led astronomers to propose the existence of dark matter.
Right, galaxies spinning too fast.
Exactly. Observations of spiral galaxies, going back to Vera Rubin and others, showed that the outer stars are moving far too fast for the amount of visible matter, stars, gas, dust that we can see. Based on gravity from visible stuff alone, they should have just flown apart.
So something else must be there providing extra gravity.
That's the mainstream solution. Dark matter. The idea is that galaxies are embedded in these vast, invisible halos of non-luminous matter that provides the extra gravitational pull needed to hold them together.
Is there other evidence for dark matter?
Oh, yes. Quite a bit now, actually. Things like gravitational lensing, where the gravity of unseen matter bends light from background objects, and observations of colliding galaxy clusters, like the famous Bullet cluster, seem to show mass where there isn't much visible matter.
Okay, so dark matter is mystery number one. What's number two?
The accelerating universe and dark energy. This is a huge shock in the late 1990s. Astronomers were using type Ia supernovae, a specific kind of exploding star that acts like a standard candle, a reliable measure of cosmic distance.
Right, for measuring expansion.
Exactly. They expected to find that the universe's expansion was slowing down due to the gravitational pull of all the matter in it. But the data show the opposite.
It's speeding up.
It's accelerating. The expansion is getting faster and faster over time.
Wow. What could cause that?
Yeah.
Something pushing outwards.
That's the idea behind the mainstream solution.
Yeah.
Dark energy. It's thought to be some mysterious form of energy with strong negative pressure, sort of an anti-gravity effect, possibly inherent to space itself, to the vacuum.
And this is a big deal.
Huge. It's estimated to make up about 70% of the total energy density of the entire universe. Way more than ordinary matter and dark matter combined.
Okay, so we have dark matter holding galaxies together and dark energy pushing the universe apart faster and faster. But we don't really know what either of them are.
Precisely. These dark sector placeholders, dark matter and dark energy, they're defined almost entirely by the gravitational effects they're needed to explain. And for some physicists and philosophers, this creates a kind of philosophical dissatisfaction.
How?
They see it as maybe being a bit like the epicycles in Ptolemaic astronomy. You know, adding extra circles to the model just to make it fit the observations without really understanding the underlying cause.
Adding fudge factors.
Some might put it that way, yeah. This profound gap in our fundamental understanding of what makes up 95% of the universe creates a kind of intellectual vacuum. Feels a bit like Newton's discomfort with action at a distance all over again. We see the effect, but the cause is deeply mysterious.
And this vacuum, this is where kinetic gravity tries to step back in.
Exactly. This intellectual vacuum has provided a new sort of impetus, a perceived opportunity for proponents of modern kinetic gravity models. They attempt to gain legitimacy by offering potentially unified solutions.
Unified how?
They essentially claim their kinetic medium, their modern version of Le Sage's corpuscles, can explain not only ordinary gravity, but also the effects we attribute to dark matter and dark energy, all with a single underlying mechanism. They're basically saying, look, you need new mysterious stuff anyway. Why not our mysterious stuff, which might explain everything?
Okay, so the Phantom returns, dressed in modern clothes. How did these modern proposals try to update Le Sage's problematic corpuscles? What is this medium supposed to be now?
Well, they reimagine the medium in various ways. Some try to use known or already hypothesized particles, maybe ultra-low energy photons or gravitons themselves acting kinetically, or maybe very low-energy neutrinos.
Things that actually exist or we think might exist.
Right. Others propose more exotic, entirely new particles, sometimes called things like quantums of gravity or A-rays, basically custom-designed particles tuned to do the job.
Making stuff up to fit the theory.
Well, proposing new hypothetical particles is standard practice, but yeah, sometimes it feels specifically tailored. And then some models even suggest a composite medium.
Composite?
Yeah, like one model called the World Universe Model, or WM. It proposes a medium of the world made up of a whole cocktail of things. Protons, electrons, photons, neutrinos. And the particles that make up dark matter itself are supposedly part of this pushing medium too.
So dark matter is pushing things around to create the effect of dark matter gravity. That sounds circular.
It can sound a bit self-referential, yeah.
Sure.
The idea is that interactions within this complex medium generate the forces we observe.
Okay, so they have these various ideas for the medium. How do they claim this solves, say, dark matter, the fast-spinning galaxies?
Well, the claim is often that they can engineer the properties of their kinetic flux, the speed, density, interaction rules of their particles, so that the resulting force law isn't quite Newton's inverse square law, especially at large distances.
They change the law of gravity.
Effectively, yes. They aim to produce a force that's stronger than Newton's predicts at galactic scales, which would make the outer stars orbit faster without needing an invisible dark matter halo. They often try to mimic the behavior predicted by MOND, Newtonian dynamics. That's another alternative theory that proposes changing Newton's laws in very low accelerations, specifically to explain galaxy rotation curves without dark matter. So kinetic models sometimes try to derive MOND-like behavior from their particle flux.
But is this predictive or just fitting the data?
That's the major criticism. Often this looks very much like scientific retrofitting. The models are constructed, parameters are tuned, with the specific goal of reproducing the already known galactic rotation curves.
So it's not like they predicted the curves before they were measured.
Exactly. It's more like painting a target around an arrow that has already landed. It doesn't really solve the mystery. It just swaps one mystery, what is dark matter, with an arguably equally complex one. Why does this hypothetical kinetic flux have these incredibly specific, fine-tuned, and convenient properties needed to match observations?
Okay, that makes sense. What about dark energy? How do they try to explain the accelerating universe with pushes?
The claim there is usually that their kinetic medium is also the source of the cosmic acceleration. The idea is that the pushing forces don't perfectly cancel out at the very largest cosmological scales.
An imbalance again.
Yes, but on a cosmic level, creating a net outward pressure that drives space to expand faster. Some models even try to get fancy, suggesting the medium causes an attractive force, gravity, at galactic scales, but becomes repulsive, like dark energy, at the scale of galaxy clusters or larger.
But again, is this just swapping mysteries?
That's the critique, yes. It's another mystery swap. It replaces the unknown physics of dark energy with an equally unknown and arguably much more complex and contrived kinetic medium that somehow has to have exactly the right properties to be attractive here, repulsive there, and match the observed acceleration rate.
And do these modern theories address the old problems, the drag, the heating?
This is the absolutely crucial point. These modern revivals almost universally fail to seriously confront, let alone solve, the classical objections we talked about earlier, the drag, the heating, the
They
self-shielding.
just ignore them.
Largely, yes, or they hand-wave them away without quantitative solutions. They've essentially just repackaged the old problems. For instance, they provide no plausible physical explanation for where the colossal amount of energy from the required inelastic collisions goes.
The heat has to go somewhere.
It does. This represents a violation of energy conservation that is arguably even more severe in these modern contexts, trying to explain dark energy and dark matter because the energy scales involved are even larger. The fundamental fatal flaws of the classical theory remain largely unaddressed. They haven't gone away just because we have new cosmic mysteries.
So while the theorists are speculating, what's happening in the lab? Has experimental physics weighed in?
Oh, absolutely. And experimental physics has been, you could say, relentlessly shrinking the space available for these kinds of alternative theories to even exist. It provides a stark reality check.
How so? What kind of experiments?
Well, one major area is the direct search for any deviation from Newton's inverse square law, especially at very short distances. Modern physics actively searches for new forces predicted by theories like string theory, which might manifest as tiny changes to gravity over small scales.
How do they look for that?
They use incredibly sensitive instruments called torsion balances. Think of a delicate dumbbell or plate suspended by a very thin fiber. If there's an extra force between nearby test masses beyond standard gravity, it will cause a tiny, tiny twist in that fiber, which can be measured with lasers.
And these are really sensitive.
Unbelievably sensitive. Experiments like those run by the UT-WASH collaboration at the University of Washington, or groups at HUST in China or NIST in the US. They could detect forces billions of times weaker than gravity.
And what have they found? Any deviations?
The results have been consistently, resoundingly null. Nothing. Gravity behaves precisely as predicted by Newton and Einstein, right down to distances of tens of microns, like the width of a human hair.
So no sign of weird short-range forces that a kinetic theory might produce?
None whatsoever. This provides a really stark reality check for any kinetic model that relies on, say, particles interacting in a way that modifies the force law at accessible scales. The room for deviation is just incredibly small.
Okay, what about the medium itself, that all-pervading stuff?
Right, the ghost of the ether. Any kinetic theory, by its very nature, requires a pervasive medium that defines a preferred frame of reference, the frame in which the particle flux is uniform. It's essentially an ether.
And didn't experiments kill the ether idea over a century ago?
Famously, yes. The Michelson-Morley experiment in 1887 was designed to detect the ether wind, the motion of the Earth, through this supposed stationary medium. Its definitive null result was a huge puzzle at the time and became key evidence supporting Einstein's special relativity, which did away with the need for an ether altogether.
But didn't people try to save the ether? Like maybe matter drags it along?
They did try. The ether drag hypothesis suggested that massive objects might drag the ether along with them, explaining the null result near Earth. But that idea was also refuted by other observations, like stellar aberration, the apparent shift in star positions due to Earth's motion, and more targeted experiments like the Hammer experiment in 1935, which specifically looked for shielding or drag effects and found none.
So, multiple lines of evidence against an ether.
Yes. The consistent, repeated failure to detect any sign of a preferred frame or an ether wind, using increasingly sensitive methods over more than a century, remains a monumental obstacle for any theory that relies on such a background medium. Kinetic gravity fundamentally requires one.
It seems like experimental reality is really boxing these theories in.
It is. And finally, there's just the ultimate challenge of detecting the kinetic gravity particles themselves. They present this fundamental paradox.
What's the paradox?
On the one hand, their flux must be incredibly intense and energetic, remember the heating problem, to produce the force of gravity. On the other hand, their interaction with ordinary matter must be extraordinarily weak and rare to allow penetration, avoid the catastrophic heating, and prevent obvious self-shielding.
So they have to be everywhere and super powerful, but also almost completely invisible and undetectable.
Exactly. It creates an almost impossible scenario for direct detection. They have to interact just enough to cause gravity, but somehow not enough to do anything else that we could actually measure, not enough to heat things up, not enough to be stopped, not enough to show up in any particle detector.
That sounds convenient for the theory, but bad for proving it.
It leads to a serious problem of unfalsifiability. If an experiment fails to detect these particles, a proponent can always just claim, oh, well, their interaction strength, their cross-section must be even smaller than we thought, or their speed must be even higher, or their properties are just different.
You can always tweak the unseen properties to evade detection.
Precisely. This endless malleability, this ability to constantly redefine the hypothetical entity to avoid experimental contradiction, is frankly a hallmark of pseudoscience, not robust physics. This phantom matter becomes defined more by what it doesn't do, by how it avoids detection, than by any positive prediction or evidence. Its properties can be endlessly shifted to ensure it remains forever undiscovered.
Okay, so wrapping this all up, where does this leave us with kinetic gravity?
Well, I think it's clear that kinetic gravity models, both old and new, are ultimately theories about a pervasive and undiscovered form of matter. And it's the required nature of this matter, its extreme, often paradoxical, and ultimately unobserved properties that seals their fate.
Right. We can appreciate the cleverness, maybe.
Oh, absolutely. We can acknowledge the laudable scientific goal trying to find a mechanical explanation for gravity and the real deductive elegance of the Fatio-Le Sage model. We can even marvel at its remarkable, though likely coincidental, prediction of the mostly empty atom. But the very properties required to make the theory work are precisely the source of its downfall. They lead directly to that inescapable the Sage trilemma: the drag, the heating, the contradictions.
And the modern attempts haven't fixed that.
No, the modern attempts, while trying to tackle new cosmic mysteries, generally haven't resolved these fundamental classical flaws. They often seem to engage in those mystery swaps we talked about, or retrofitting models to match known data, largely disconnected from the stringent experimental constraints and the consistency demanded by the rest of modern physics.
So what does this whole story, this journey through push gravity, tell us about science itself? Is there a bigger takeaway?
I think the story of kinetic gravity is a really powerful reminder. It shows that even the most intuitively appealing or seemingly elegant explanations must ultimately bow to the full weight, the full breadth of empirical evidence and theoretical consistency. An idea isn't right just because it feels right or explains one thing neatly.
It has to fit everything else we know.
It has to fit everything. So it really asks us to consider, how do we, as scientists and as curious people, distinguish between a truly revolutionary idea that's pushing the boundaries in a productive way and one that is simply, well, a fascinating intellectual cul-de-sac, a road that looked promising for a while but was ultimately not taken for very good reasons? What stands out to you about how science manages to self-correct even when an idea seems appealing?